Let's build some very fundamental and very intuitive statements that we can say about some well-behaved functions. So let's throw out some disclaimers here. Let's let B and C be real numbers and let's let N be a positive integer. And we're going to write three statements here. And we're going to use these kind of as building blocks when we start evaluating limits directly. But we need to establish a couple of very simple and intuitive truths. So B and C are real numbers. N is going to be a positive integer, and we'll use it for our third and final, kind of the building blocks here of these limit properties. The first statement we want to say is that the limit as x approaches C of a constant value B. Think about what the graph of a constant value looks like. It's a horizontal line that stays constant through whatever that value B is. So for example, when you graph the line y equals 5, you know that's a horizontal line that just cuts through 5. Well, no matter what I'm approaching on the x-axis, this constant function is always staying constant. So the limit as x approaches C of B is always going to equal whatever B is. So for example, if I have the limit as x approaches 2 of -5, that -5 is never going anywhere. So it doesn't matter if I'm approaching 2, it doesn't matter if I'm approaching 3. The limit as x approaches anything of a constant is always going to equal that constant value, in this case, -5. So that's our first building block. Our second building block here, let's take a look at the limit as x approaches C of the function x. So think again back to your Algebra 1 days when you learned about the linear parent function y equals x. Well, one of the things you knew was that no matter what the x input was, the y output was always the same thing. And that's why you always saw points like 2, 2, or -3, -3. So again, it doesn't matter whatever this C value is. If I'm just talking about the linear parent function y equals x, whatever value of C I'm approaching, I'm getting that same output back. So the limit as x approaches C of x is always equal to C. And I can state that and say the limit as x approaches 4 of x. Well, as x is getting really close to 4, this function y equals x, the output is also getting really, really close to 4. And I can do that for any value of this C right here. The third and final building block, let's throw some exponents and some powers into it, and that's where n is going to help us out here. So the limit as x approaches C of x to the n power. So again, as long as n is a positive integer, now then, if it was a rational, if we had a rational power right here, we might have to address some things, but as long as n is a positive integer, remember, if it was a negative integer, it would be putting x down into a denominator. But we're talking about functions like x squared, x cubed, x to the fourth, continuous functions where nothing weird happens. I can say that as I'm getting really close to C, I'm just approaching the function values of x to whatever power. And so this ends up equaling C to the n. And so for an example, if I look at the limit as x approaches 2 of the function x cubed, think about what x cubed looks like. You know the parent cubic function. As x is getting really close to 2, because nothing weird happens with that function in terms of holes or jumps or anything else that we've seen in the last couple of lessons, the limit as x approaches 2 of this function x cubed is going to simply equal 2 cubed, which is 8. And these three building blocks of a constant, of an independent variable x, and x being raised to a positive integer power, they're going to be really powerful statements when we start evaluating limits analytically.